Okay, in the last class we looked at a simple expansion chamber muffler of this kind with an inlet duct and an outlet duct which is going to infinity in both directions, and the expansion chamber had an area of cross section S2, whereas the inlet and the outlet had an expansion had an area which is S1, and we said that S2 by S1 is equals to n, which is greater than 1. Okay. And we took the transfer matrix at each of the sections. This was our first section, this is the second, this was the third, and finally, this was the fourth, right. So, effectively the transfer matrix between 3 and 4 and between 1 and 2 are identity if we frame it in terms of mass velocities rather than particle velocities. So, the transfer matrix would relate the state variables at station 4, which is P4 V4, with the state variables at station 1, which is P1 V1, and here you will have the entries as cos KL, cos KL, I Y sin KL, and here we had I by Y sin KL, right. Just to make sure that we do not confuse between the two y's, remember that the cross section area in there are two cross sectional areas that we are talking about. The cross sectional area of the expansion chamber is denoted as S2, the cross sectional area of the inlet and the outlet are S1, right. Accordingly, the characteristic impedance in both these segments will be different. The characteristic impedance in the expansion chamber segment will be marked as Y2, and the characteristic impedance in the inlet and the outlet will be marked as Y1. Okay. So, just to make things specific, we will put a 2 subscript along with Y, because the Y that we are talking about is due to the expansion chamber, and we will call it as Y2 rather than keep it open as Y, because we will see another Y1 coming due to the expansion chamber. So, this is roughly where we left. We also realize that in this portion there is going to be only one wave that is going to be transmitted outwards, but in the inlet section there will be an incoming and an outgoing wave, right. So, A plus B together should give us P4, and A by Y1 minus B by Y1 should give us V4, right, or A minus B should give us as V4 into Y1. That was the relation that we could have, and also in the other outlet section we had P1 as the outgoing wave, which means that the mass velocity in the outlet section is going to be P1 by Y1. Okay. So, that part was understood. Now, what we will do is we will open this matrix equation up. So, this would mean P4 cos KL P1 plus I Y2 sin KL into V1, but V1 is P1 by Y1. So, I could as well write this as P1 by Y1 over here, right. So, this is P4, but then P4 is also known to be A plus B. Okay. So, A plus B is now related in terms of P1, right, which is the final transmitted wave. And similarly, if we open out V4, this V4 is given as I by Y2 sin KL P1 plus cos k L into V 1, but V 1 is P 1 by Y 1, right. So, this is what it comes, and V 4 also has been already written as A minus B divided by Y 1. Okay. So, in other words, I could simplify this equation to be A minus B is equals to I times Y 1 by Y 2 sin k L into P 1 plus cos k L into P 1, right. So, this is A minus B, and we had already formed the equation of A plus B. So, together we should be able to find A and B in terms of P 1. So, that is the next job which we will do in the next page. So, collecting the two equations once again, A plus B is given by this expression, okay, and A minus B similarly is given by the other expression, so therefore, it is clear that A by P 1 is going to be cos k L plus I by 2 y 2 by y 1 plus y 1 by y 2 into sin k L from these two equations, right. And please recall that y 2 is C by S 2 and y 1 is C by S 1, S 2 and S 1 being the area of cross section of the appropriate portions of your exhaust line, right. So, therefore, this fraction y 2 by y 1 would read as S 1 by S 2, which is 1 by n lesser than 1, and similarly y 1 by y 2 is n, which is more than 1. So, as a result, A by P 1 is going to read as cos k L plus I by 2 n plus 1 by n sin k L, right. And this is exactly what I mean, this in terms of the logarithm is exactly what is transmission loss, because what is A and what is P 1? A is the incident wave, P 1 is the outgoing wave, because in the outlet section there is no other wave, there is only a transmitted wave which is going in the outlet section, and we defined this ratio to be the transmission loss. So, remember transmission loss, recall transmission loss was defined to be, and I will abbreviate this as TL, to be 20 log base 10 A by P 1, modulus of it, right. You cannot take the real or imaginary, you should take the modulus of it. So, now we see that we have actually sitting right in front of us the expression for transmission loss. This, remember, we were unable to do it with a hand calculation in case of method 1, wherein we took all the 4 waves, 4 or 5 waves, whatever that was, and it led to a system of 4 by 4 equation. We left it at that point saying that the equations have been obtained, one can solve those equations using a computational package, but we are saying that the transmission loss can be readily given as like a formula if we appeal to the transfer matrix method, which is the second method that we are going through. But more than the formula, what is very interesting to realize is that we will take some special cases out of this and try to figure out how the plot of this transmission loss will look like. So, this is the formula for the transmission loss, you will recall. What we wish to do is that we wish to make a plot of transmission loss against frequency. You know, k is the parameter which obviously changes with frequency, right. So, the non-dimensional frequency will be denoted as KL. This is very important. You should not always talk in terms of dimensional terms. Sometimes non-dimensional analysis is far more generalized and it will give you much more insight than dimensional terms. Please understand, for a fixed length, KL changing basically implies frequency changing, right, because k is directly proportional to the frequency omega. So, non-dimensional frequency is KL. So, there are very many interesting cases. First, let us try to understand what happens at KL equals to pi and 2 pi and 3 pi. What happens at these values and 4 pi? At these values of KL, sign of KL will go to 0, right. So, at KL equals to n pi, I should not use n because n stands for something else in this analysis, m pi, m is 1, 2, 3 whatever. So, if KL equals to m pi, then sin KL will go to 0, cos KL will be plus or minus 1. So, therefore, A by P1 magnitude of it is going to be 1. So, therefore, A by P1 magnitude is going to be 1, and what will be the transmission loss? 0. So, the transmission loss for these frequencies, these non-dimensional frequencies are supposed to be 0. There is actually no transmission loss. Whatever is the incident wave amplitude A, the transmitted wave amplitude remains just the same. So, the muffler is completely ineffective at these frequencies. It is not working like a muffler, whether it is there or whether it is not there, it does not make a difference, because it completely transmits the incident wave, right. So, this is very interesting to note that TL is going to go to 0, transmission loss goes to 0. What happens at the other intermediate frequencies? Now, KL is equals to 2 m plus 1 pi by 2, right. So, if you now take the other intermediate frequencies, that is odd multiples of pi by 2, right, then the cos scale term will vanish and the sin KL will remain. So, sin KL is going to be either plus 1 or minus 1, does not matter, because when you take magnitude it is anyway going to get to plus 1. But now you get to see that A by P1, the magnitude of this is going to be n plus 1 by n, right. So, that means if n, which is the ratio of the cross sectional area between the expansion chamber and the inlet and outlet is rising, what happens to n plus 1 by n? That also will rise, right. So, therefore, transmission loss will also be high, right. So, at these numbers you can expect that you will get a maximum of the transmission loss. So, the transmission loss curve will look something like this, right. So, the maximum will happen at odd multiples of pi by 2, pi by 2, 3 pi by 2, 5 pi by 2 and so on, right, and all of those maximums will be at the same height. You can plot this to verify my statement, and if you change the value of n to a higher number, then you will get more height of these lobes. The lobes will further increase in height. So, you will get more transmission loss if you have more height, sorry, if you get you will have more transmission loss if you have more, if you introduce a further high change of cross sectional area, you will get more transmission loss. So, in my drawing, in red I would have plotted for N2 and in blue I would have plotted for N1 and then N1 is less than N2, right. So, if you introduce large cross sectional change, you will get larger peak values of transmission, but the nature of this curve will look exactly like this, right. So, this is the transmission loss versus frequency curve. Now, how do you make use of this fact in the design of exhaust system and design of muffler systems for exhaust? The answer lies in this fact that please understand that if your exhaust noise happens to show frequency content around these values where KL equals to pi, then this expansion chamber muffler is useless. Okay. So, you should rather choose an L. So, remember L is a design parameter. You could this length of the expansion chamber is your choice, what you give as the length of the expansion chamber. So, the idea would be to first determine what is the frequency of your interest wherein you have an exhaust noise problem, determine the corresponding wave number and then choose the length such that KL becomes pi by 2 or 3 pi by 2 or 5 pi by 2, whichever is feasible. Obviously, you would like to keep the length as small as possible, but you cannot make it very small. So, make it choose this value L such that KL happens to hit an odd multiple of pi by 2. What is a bad design is that if KL happens to hit even multiples of pi by 2 or KL happens to hit pi or its multiples, right. In that case, whatever area of cross section change that you choose will render itself ineffective for the control of the exhaust noise, because the transmission is just complete at those frequencies. But the first thing is choose the length of the expansion chamber such that you are at KL equals to pi by 2. The second thing is that give as much expansion as is possible. Okay. Choose the expansion chamber area to be as high as possible such that your N value is also increased. With a higher N value, which is the ratio of area between the expansion chamber and the inlet and outlet duct, you are supposed to get a higher transmission loss, right. So, if you give a higher expansion ratio, you will get a higher transmission loss. So, these are like two elementary design guidelines which arises in the principles for design of exhaust muffler. But then when I say high expansion is preferred, so you give as high as possible 100, 200, what stops you from giving a very high cross sectional area? Space. One is space, definitely you cannot give a very high area for the expansion chamber because the ground clearance in the vehicle will not permit so. But let us say you are talking about a tractor where the muffler is actually on the outside, right. Muffler does not go on the ground, it goes upwards. So, there is no space constraint. So, what prevents you to put a very large expansion chamber in a tractor? Back pressure, right. So, please understand that this very important aspect, that a large expansion ratio is favorable in terms of acoustic transmission loss. However, a large expansion ratio leads to back pressure, which is detrimental to the engine performance. Okay, let me just explain this second aspect a little more. So, remember the purpose of the exhaust line is twofold. I mean rather the primary purpose of the exhaust line is to make sure that the burnt out exhaust gases do escape from the engine into the atmosphere, right. Now, obviously, at the atmospheric outlet you have exactly atmospheric pressure. This time I am talking about mean flow, I am not talking about the acoustic component of the fluid flow, I am talking about mean flow. Okay. So, you have exactly the atmospheric pressure, as you know from principles of fluid mechanics, that when you have a mean flow happening through a pipe, because of the viscosities that are there in the flow situation, there will be a pressure drop as the flow happens through the pipe, right, which means the pressure at each progressive station would be higher, right. So, P1 must be higher than P0, only then the flow mean flow is going to happen, otherwise the mean flow cannot happen. Similarly, in fluid mechanics it is well known that when you have a sudden contraction or a sudden expansion, either way you suffer some head losses, right. I mean the flow suffers from some head losses, which means at each of these progressive stations the pressure must be higher, so that the mean flow can happen, because associated with each of these cross sections there are head losses. The head losses due to a pipe flow, the head losses due to sudden expansion, the head loss due to sudden contraction, which means that finally, if you look at the engine outlet condition, which I can say it as station 5, this P5 will have to be greater than P4, will have to be greater than P3, will have to be greater than P2, will have to be greater than P1, will have to be greater than P0, but P0 is forced to be the atmospheric pressure, which means if you make a higher expansion ratio, this difference between P3 and P4 and similarly P2 and P1 will keep cropping up. You cannot change this ordering by any means, this is God given, this is, as I said, this is for the mean flow through the exhaust. Okay. So, for mean flow through the exhaust, you must have this situation asserted. So, now what happens is that if you use a large expansion chamber, then P5 is definitely, or the pressure at the outlet of the engine will be very large. And what happens if the pressure at the outlet of the engine is very large? The exhaust gases will not find a way to escape. It is like someone will block the escape of exhaust gases. So, some part of the exhaust gases may actually not escape, but tend to reside back in the combustion chamber, at least partially, right. How will that affect the performance of the engine is easy to understand. If you have the combusted gases, the burnt out gases not getting evacuated from the engine, they will definitely deteriorate the combustion process in the next cycle, right. So, the combustion process in the next cycle will be much less in efficiency, because now part of this combustion chamber is actually filled up not with the new fuel air mixture, but with the old fuel air mixture which is already burnt up. So, therefore, the efficiency will go down drastically. So, therefore, engine designers will not permit, for the sake of efficiency of their engines, will not permit a build up of the back pressure. They will have a hard constraint which you cannot defy, that a back pressure for the engine should be kept within a certain norms. So, as I said, sometimes our NVH requirements is more a refinement than a design stage solution. So, you have to wait for that guideline to come from your engine designer or whoever the engine vendor is, and then you need to choose your muffler such that it does not conflict the back pressure requirements of your engine. Otherwise, if you are doing a muffler design in isolation, or if you are really putting a muffler such that the noise which is you record the noise from the engine, put it in a speaker and play it out, then you will actually see that a larger expansion chamber is obviously better, provided the space permits. But I think even in commercial vehicles at times space is not a problem, you have lot of space to put a large expansion chamber, but what becomes a problem is this efficiency issues of the engine, right. So, based on these two considerations, one has to choose these consideration, the optimal expansion ratio needs to be chosen. Okay. So, this is about the one of the simplest form of exhaust muffler, that is the expansion chamber mufflers, but obviously there is much more to it than meets the eye at this stage, and we will come to the definition of some more technical aspects, but before we do that we will take few steps backwards and we will try to put this muffler design context in a very important perspective. The way this field has evolved is that there is lots of machinery that actually has been borrowed from electrical circuit theory, and even if you look at the mechanical vibration theory, there is lots of analogies, very interesting analogies which comes between mechanical vibration and electrical circuit theory. So, it is true even for the acoustics, because acoustics has sort of spun off from the vibration theory also. So, much of these ideas related to impedance has actually cropped up or has actually been introduced in the context of AC circuit theories, and we will make good use of these circuit theories and be able to take a little more detailed analysis about mufflers, where we talk about insertion loss. Till now we have been talking about transmission loss, but possibly a better design quantity is the insertion loss. So, before I introduce to you these ideas of insertion loss, I will just take a few steps backward for a few classes and talk about electromechanical acoustic analogies. Okay. This is something which is very classical. It is very old, but for some reason it has not found much flavor in as of today. Somehow for some strange reason which I do not know why, I do not think we are using this analogy techniques so very effectively, but maybe things will change with you. So, let us just quickly go through these ideas one by one. So, one way to do the analogy is obviously something probably you would be aware of. So, given a spring mass system, you would know that this spring mass system has the same set of equation as this LC circuit, and with a damper it also becomes like an LCR circuit. So, this is L, this is C, this is R. Okay. So, this part of it is usually given in books, and therefore, I would not reiterate much. If you just write the equation of this spring mass damper system driven by harmonically forced oscillator F, that equation will turn out to be exactly the same as the LCR circuit driven by an AC harmonic voltage source F. The analogy being that the charge is going to be equivalent to the displacement, the velocity of the mass is going to be equivalent to the current in the circuit. Okay. But then what probably is not talked about is what happens when you have an interconnected system. Very rarely do we experience systems which is just like a single degree of freedom spring mass system. More often than not, we are encountering situations which are collection of such spring mass systems, right. And we want to have an electrical circuit theory analog wherein you have an electric circuit which is analogous for a assembly of connected spring mass systems, right. And we need a step by step methodical approach by which we can construct such electrical circuit analogies. Obviously, if you have a multi degree freedom system, then it is very difficult to contemplate by looking at the equations one after the other and coming up with that AC circuit which exactly resembles the equations of the multi degree of freedom mechanical system. We need a little more elegant approach than such a naive method, which is what I will directly jump into. So, towards that end, let us get our building blocks in place. So, the first building block is that of mass, right, in a mechanical system. Now, please note that we are this is what we will call it as two port elements. Okay. So, whether it is a mass or it is a spring, it has an input and an output, right. And what we are interested in is to again relate the force and velocity at the input end of these mechanical elements to the force and velocity at the output ends of these mechanical elements. So, here again just like we introduced to the transfer matrix method, we would like to understand how the force and velocities. So, let us call this F1 and this as I will indicate velocities by dotted line and I will indicate forces by solid arrows. We wish to understand how the forces and velocities at either side of this mechanical element, the left and the right end of the mechanical element is related, right, both for the spring as well as for the mass as well as for the damper. Okay. So, we would like to relate just like transfer matrix method, we would like to relate how V2 and F2 is related to F1 and V1 in each of these cases, right. So, can we quickly do it? For a mass element, what is it that happens? What can you say about V1 and V2? You have a mass element and you are talking about V1 which is on the right face of the mass and you are talking about V2 which is on the left face of the mass. How should V2 and V1 be related? They should be equal, there is no other way out. V2 should be equal to V1. How about F2 and F1? Should they be equal? Why? Can you not apply two different forces in the two different directions? Yes, you can, right. There is nothing which is stopping you to apply two different forces on the two different direction. You may say then the mass will fly away, so be it at this stage, but there is nothing which is stopping you to apply two different forces at the two different faces, right. But actually it will not fly away because this mass will be connected to a spring and this spring will be connected to another mass and eventually something will get constrained. So, the concern of the mass flying away will actually not turn out to be a realistic concern, right. But physically there is nothing which forbids us to apply two different forces to the mass at the two different faces. But then how is the forces and the velocity? So, in general F1 need not be equal to F2, right. But then how do you relate the forces with the velocities? So, this V2 equals to V1 equals to V, let us say. How do you relate the forces with the velocities? Good old Newton's law says that mass times rate of change of velocity is equals to total force, right. What is the total force? F2 minus F1, right. That should be equals to mass times dV dt, right. But then if you come to the harmonic assumption, which is what we have been doing, dV dt is j I omega times V, right. Any ddt operator can be replaced with I omega using the harmonic assumption. So, F2 minus F1, or in other words the change in force from either side delta F is going to be I omega m times V, or in other words delta F by V is going to be I omega m, and this quantity we would like to denote it as Zm. This is like an impedance, okay. This is like an impedance and we would call it as Z subscript m. What was impedance in the acoustic parlance? Pressure by velocity. Here the pressure is being replaced by force, makes sense, right, because pressure is after all force per unit area, right. So, therefore, if you have to write this as a transfer matrix, how do you write it? F2 V2 has got to be equal to some matrix multiplying F1 V1, V2 is equal to V1, which means on the bottom row I can write it as 0 1. What happens in the top row? 1 Zm, right, because Zm times V is equals to delta F. What is delta F? F2 minus F1, that is exactly what you get as first equation. So, all these elementary ideas coming out of our fundamental mechanical system, that is mass, is captured through this simple transfer matrix relation, which is going to read as F2 V2 is equals to 1 0 Zm 1 F1 V1. Note that this is the structure of the transfer matrix for any mass element. If it is a mass element, this is what the structure of the transfer matrix should be. Now, how do you make an equivalent circuit for this? The equivalent circuit will be exactly this Zm in line, and we have a ground line, and so if this potential is F2 and if this potential is F1 and the current flowing is V, which is equals to V2 is equals to V1, then F2 minus F1 is exactly V times Zm. This is exactly the circuit that we have been looking for, because all that I am trying to say is that this mass element gives this transfer matrix, which basically says that the velocities at the input and the output of this element is going to be the same, as we know that the velocities are analogous to current. So, therefore, if you put an impedance in this fashion, the amount of current which is entering the impedance element should be the amount of current which is leaving the impedance element, which means that V is equals to V2 is equals to V1, right. And similarly, the drop in potential as this much current is flowing across this impedance is given by V into Zm, which is delta F. So, this also says that delta F has got to be, which by definition is F2 minus F1, has got to be V times Zm, right. So, therefore, this is the equivalent circuit corresponding to the mass element. Now, let us do the spring element also parallelly. So, for the spring element, this is the situation. First, let us understand, is there any quantity which will remain constant between the two ends of the spring element? Is it expected that V2 and V1 has got to be necessarily the same? No, the two ends can have different displacements and hence different velocities. So, in general V2 is not equals to V1. How about the forces? The spring must transmit all the forces that it gets, right. So, for the spring we will say that the spring will transmit all the forces that it is supposed to get. Spring is a transmission element, right. So, F1 is equals to F2. So, here it is the other way around, the force is getting transmitted, but the velocity is being unequal, right. So, F1 is equals to F2 is equals to F, let us say, but then how are the forces and the velocities to be related? We know that the force has got to be the spring constant times x2 minus x1, right. But instead of talking in terms of the displacements x2 and x1, we wish to talk in terms of velocities, but then the displacements and velocities are related by a factor of j omega, right. So, this will be j omega in the denominator now, because basically we are integrating, not differentiating. From velocity to acceleration we had to differentiate, from velocity to displacement we had to integrate, which means instead of putting j omega in the numerator we will put j omega in the denominator. So, that becomes k times V2 minus V1, right, and this could also be taken as k times delta V by j omega, right. Delta V is the change in velocity between the input and the output ports, just like delta F was the change in force between the input and output ports, delta V is the change in velocity of the input and the output ports. So, therefore, finally, we get F by delta V is equals to k by j omega, and just like electrical people do, we would change over from stiffness to a compliance notion. Okay. So, K is 1 by C, C is called the compliance, okay, reciprocal of stiffness, and this we can denote it as ZS. This is also another form of impedance, that is a ratio of force and velocity. But please understand that between the mass and the spring there is a very important difference. In the mass we are taking the velocities as same, forces are different, and therefore, the impedance is the ratio of change in force to the velocity of the mass, whereas for the spring it is the other way round, we are taking the forces at the input and the output to be the same, and now we are saying that the velocities are different. So, force divided by the change in velocity, right. So, that quantity as we have calculated is 1 by j omega compliance, which is equals to ZS. Now, what would be the transfer matrix for this situation? F2 V2 has got to be related to F1 V1, right. The top row is simple to write because F2 is equals to F1. So, 1 0 on the top row this time, that is almost trivial. What happens to the next to the bottom row? The bottom row says that you must have V2 minus V1 to be equals to F by ZS, right. So, therefore, V2 minus V1 has got to be F by ZS. So, therefore, 1 by ZS has to come here. So, this is the transfer matrix for a spring element, right. What about the circuit for the spring element? The circuit for the spring element can be similarly derived. Now, you want the potential at the input side of the electrical element to be same as the potential at the output side of the electrical element, right. So, therefore, if the potentials have to be remaining the same, so therefore, what I am drawing on the bottom is the ground line, what I am drawing on the top is the active line or the line which has the voltage. So, voltage 0 is the ground line, okay. So, therefore, now what we want is that on either side of our electrical element you should have the potential being same, which means the element should be in a shunt position. So, this is our element ZC. So, this will ensure that the voltage across the input side and the output side is same, right, whereas the current is not the same, because a part of the current would have gone in the direction of the shunt, right. So, this is V2 minus V1. So, again you can verify V2 minus V1 into ZC is becoming F, right. Oh, I should call this ZS, yeah, ZS is what we have defined. So, V2 minus V1 into ZS is basically F, which is again coming out from circuit theory. So, both for spring as well as from mass we have derived the circuit, we have also derived the transfer matrix, right. What about a damper? That should not be difficult. Again, damper is a 2-port element, right. This is how we denote a damper. Just like two ends of the spring can have relative displacement, two ends of the damper also you realize can have relative displacement, right, but the force has got to be transmitted. So, whatever is the force that is coming in must also go out, right. So, therefore, we have F2 equals to F1 is equals to F, but V2 minus is not necessarily equal to V1, and the total force, whether you call it F1 or F2, so I will just call it F, is equal to C times V2 minus V1. So, that again means F by delta V is equals to C, and this we could call it as ZR or the resistance. Please note that the impedance for the spring is imaginary, the impedance for the mass is imaginary, but the impedance for the damper is real, right. And remember, again picking up from electrical terminology, real part of impedance is called reactance, and imaginary part of impedance, sorry, real part of impedance is called resistance, and imaginary part of impedance is called reactance. Okay. So, here you have the case that the impedance is virtually a resistance element, it is actually an energy dissipation element. This is very important to understand. Remember, in the acoustic parlance we had seen this, when the intensity is having a real component, it is actually showing that there is a time averaged power that is flowing out from the system. Same thing happens in circuits, or same thing happens in mechanical elements also. Okay. So, how would you put the electric circuit? It is just the same, you have to put it in shunt position with ZR as the equivalent impedance. So, this is F2, this is F1 and this is the ground line, and here it is V2, I should use the dotted lines. There is a V2 current which is going in, but there is a V1 current which is going out, which means there is a V2 minus V1 which is flowing into the shunt element. That means, V2 minus V1 into ZR must be equals to F, or the potential difference, right. So, this completes our derivation for the 3 primary mechanical elements, the spring, mass and damper. Next class when we meet, we will do lots of examples of how to combine these spring, mass, damper elements and build up any arbitrary combinations to draw the electric circuit and also the transfer matrix method. The electric circuit and the transfer matrix method actually go hand on hand. So, the transfer matrix method is just the mathematical representation, but the electric circuit theory is a very powerful tool by which you can interpret the results, and especially when we come to source impedance and radiation impedance, we can now therefore talk about in very easily when we introduce this methodology. Please understand, I will repeat this once more, that the transfer matrix for the spring element, the mass element and the damper element transfer matrix I have not written, I will quickly write that part. What would be the transfer matrix for the damping element? It will be exactly of the same form as the spring element, right, nothing changes, just that I have to replace ZS with ZR, right, that is all. So, this is the structure of the spring element, or the structure of the transfer matrix for the spring element, for the damping element is same, whereas the structure for the mass element is in sharp contrast, right, whereas the transfer matrix method can have an arbitrary structure, right. So, this is basically a very important observation to note at this point. As we go higher down the line, we will be able to elaborate this difference, but at this stage you can note that these lumped elements will have a very specific form of the transfer matrix method. In other words, what it means is that if the transfer matrix method is a generic, if the transfer matrix has a generic structure which does not conform to one of these structures, then you cannot have an electric circuit of this kind, you simply say that it is a distributed circuit. Okay. So, that is also possible. All these things we will do as we go along.